Hello, everyone. I hope everyone's having a good day. Today, we're going to do a really quick video on how to take the next step from a bouncing ball animation to a simple harmonic motion. So, what is a simple harmonic motion? So, if we think about it in terms of physics, we can really quickly imagine it as a pendulum which oscillates from its equilibrium, just like that, using some laws of motion. And I am not going to go into the details. I hope you can research into how it's actually derived. But the equation itself that we're going to use for this video is this here. The theta t equals theta naught times cos omega t plus y. So that is telling you what angular displacement is displaced from a phi angle. And we have your omega t and a constant theta naught. The omega, which is our frequency, or the angular frequency, is defined by this little equation here, square root of g by the length of the pendulum. So you can kind of imagine how a longer pendulum or a smaller pendulum can have the effect on the theta t. And these are things that we would then initialize. So you have your parameters, which are your capital L, theta naught, omega, and your phi. And for the purpose of the simulation, we have to define our time steps and time interval. Let me just quickly jump into the code just to show you what's happening. And I hope you can see this. So the first few things are pretty much routine. We load our libraries, we initialize our parameters, initialize our time vectors, and these are all just random that I thought was a good number that I've picked. A next step, if someone would be interested in, is building a dashboard, a shiny dashboard, where you can put all of this into a input box where people can change and play around to see how the pendulum reacts to that. So the first few things we need to define is our data frame. So we're going to define a few things here first. We have our time, which is our time vector, the angle itself that it's going to be displaced, which we saw in the early equation. The other two things we are going to define here is the x and the y coordinates. So the x and the y coordinates tell you the point of the pendulum that is being shifted on the coordinate system. And we can define those coordinates based on the angle theta naught times cos omega t plus y. And the way we get this result is just by using some basic trigonometry. We resolve the vertical and the horizontal coordinates, and we get this very nice looking equations. So let's just run that. We get our data. We define a fixed point for the pendulum. So it'll be just a 0, 0. And you can define it wherever you want it to be, but then you will also have to make sure your end of your pendulum is kind of proportional to that. So now we get to a plotting stage. So few things we need to take into consideration. We define our x and the y's here, which will be used for the firstly for the length of the pendulum, which will be our 0, 0 start and the end of the x and the y from the data frame. We also have the jump point, which will be our red ball, which will be attached to the end of the segment here. And what we could do is, to make it a bit more interesting, is to trace the path of the pendulum. And ggplot gives you a very cool function called jump path. We can just jump path. We could literally color it blue and then label the x and the y coordinates. Sorry, x and the y labels. Fix some limits in there, and then transition based on the time. So that will be how our GIF will be animated. If we now just run the plot itself, this would create the animation. It takes around 10 to 5 seconds. And once it renders through, we get this really cool looking plot, which is very much a simple pendulum that is oscillating from side to side. But for me, it's very fascinating to see how someone could define your physical loss of motion, put that into a programming language like R, which is a statistical computing language, and R has enough features in it to create a really cool animation like this. And these are things we would use specific software in our physics degrees, which I did ages ago. It can be recreated now, and I just want to take it to the next step now. Like, what are the limitations of this animation? Can we do even further, more interesting simulations here? What sort of mathematical or physical models can you build in R? Because R is pretty much a statistical language. Not much physical modeling is done from what I am aware of. But if you do have comments about it or have worked in that field, please let me know. It would be great to see how people use this in that kind of situation. So I hope you guys have enjoyed what I've just shown, and see you guys next time. Thank you.